Hi, I'm Will Martin, and this is going to be the final demonstration for ECE 574, a special topics course related to software migration. So here you can see my Microsoft Visual Studio C++ project, but we're not actually going to use this to launch my application. We're going to go over to this release folder, so we have an executable here. So we'll double click the executable, and that pops up the GUI and the main interface for my application. You can see first we have a little title box up here just giving you some basic information about the application. We also have two clickable sets of buttons. One if you want to enable Android to interact with the system. We're not going to do that this first time though, we're just going to run the system on the computer. In this box over here you have the pose estimation output, so you know your X, Y, and Z coordinates in 3D space and your alpha, beta, gamma, roll, pitch, and yaw angles in 3D space with respect to the camera. Over here we're going to show the time per iteration and the current frame rate in seconds. Along the bottom we're going to have our two input images, one where the lasers have been turned on, one where they've been turned off, and then the difference image between the two. So I'm going to go ahead and start the system now. I'm clicking start tracking. It takes about 2 or 3 seconds to load everything into memory, but once we have those initializations complete, you can see that we're running at a fairly decent clip. We've got a frame rate of 3.3 frames per second. You can see that we're successfully extracting the 4 points of the quadcopter and correctly labeling them front, back, left, and right in each frame. You can see that our frame rate holds fairly steady here, and that our time per iteration is just under 300 milliseconds. So in this configuration, the statics were about 1.5 centimeters to the right of the camera, 4.4 centimeters below it, 111 centimeters up in on the z-axis above it. And a little hard to tell from the image, but we do have a slight roll to the right, a slight pitch forward, and a yaw angle of 180 degrees indicates that the quadcopter is facing due south of the camera. So just to see it in action a little bit more, I'll give the quadcopter a little tap here, and we can see that even when it's moving around, it still is successfully tracking. Also notice that the time per iteration does not increase. You will notice occasionally that instead of having 3 green circles and 1 red circle, that we'll have a set of yellow circles that are unlabeled. If I disturb it a bit more, those will be more likely to pop up. But every once in a while we get a point in the difference image over here that is confused as one of these 4 circles that we're trying to extract. We have a feasibility check that we run our set of 4 points, and if it turns out that one of the points that we're getting is not from one of these 4 expected points, then we don't accept those as the set of 4 points of the quadrangle, and we render those circles yellow instead of green and red. You can also notice that we have an indicator light at this position on the GUI, indicating that we have active tracking on. If I obscure one of the lights, we're no longer doing pose estimation, so that the light turns red, the active tracking indicator, and then as I take my hand away, the indicator goes back to green. Let me move the mock-up around in 3D space a little bit. So first thing I'll do here is move it up, and we'll see the Z position in centimeters go up from 112 to 120, 130, 140. Similarly, if I move the quadcopter down and keep it in frame, you can see the Y position increases negatively, and similarly if I move it to the left, the X position increases. I can pitch it forward and have that roll angle increase negatively, or the pitch angle. I can also roll it to the side, and you can see that angle is now largely negative. I'll roll it the other way. Now the angle is positive. If I rotate it, the yaw angle will change. And that is a basic demonstration of this system operating under a C++ engine, and that concludes this demonstration. I'm going to take one other brief video showing interaction with an Android device.